Hi, my name's Andy Rudoff, and I work for Intel. But at these conferences, these SDC conferences, I really wear two hats. One is my Intel hat, where I'm the persistent memory software architect. But the other is my membership in the SNIA NVM programming technical work group, the TWIG, where I helped define the persistent memory programming model. And you'll see this as a theme throughout this talk, where I talk about general abstract concepts that we came up with in the TWIG, and then I'm going to relate them to the more concrete implementation that we've done on the Intel hardware to help show how these things work. This talk is about persistent memory programming in a way where you can avoid all the cache flushing that has become characteristic of persistent memory programming. That's the general concept. And then you may notice in the title on the agenda that it referred to EADR, which is the more specific implementation of one way of doing that on the Intel platform. So I'll be describing that in more detail in a few slides. I'm going to start out by giving some what I consider the essential background here. First of all, with my SNIA hat on, when we formed the TWIG, we had to decide, what is persistent memory? How would we define it? And after some discussion, we really boiled it down to 2 points. It's byte addressable persistence, and it's so fast that it's reasonable that you would just wait for the data when you do a load from it. Unlike storage, where you're more likely to say, this operation is going to take a while, so I'm going to context switch away. I'm going to do some other work unrelated to this, and when the data arrives, I'll context switch back. My definition of persistent memory and the TWIG's definition is, well, it's reasonable for you to just wait because it's so fast. You might as well not spend time context switching away. I know that's a bit vague, but it basically defines the programming model when you do it that way. Otherwise, if you're switching away, it's really just the storage model, right? And then we also defined how persistent memory is exposed to applications in this document we published called the NVM programming model. And persistent memory is one aspect of that document. The programming model itself has been described, well, for at least 6 years now at SDC. I keep bringing this slide, and so I'll go over it quickly, but you'll see in a moment, I'm really gonna focus on one specific type of programming with persistent memory. In our model on the left here, you'll see the management software here is able to manage persistent memory and check its health and so on. That's out of scope for what we're talking about today. But in the middle, you'll see how persistent memory can be used as storage. These are unmodified applications using the standard APIs, unmodified file systems, and it's all made possible by some sort of generic persistent memory driver in the operating system that knows how to talk directly to the load and store interface to persistent memory. So in this middle path here, where things aren't modified, they just think they're talking to storage, I like to say, you're just using persistent memory as if it's an SSD, a simple, storage device. It just happens to be really fast, low latency, and so on. So not too interesting there because there's not much to do. You just use the standard storage APIs like you always have. Now, over on the right here is where we're going to focus more today. This is where it gets more interesting, where you have a persistent memory-aware file system in your operating system. And my definition of a persistent memory-aware file system is one where you're still supporting the standard file APIs, open, close, read, write, but you're not using the page cache. You don't read blocks into DRAM in order to access things. If an application does one of these operations, you can see it. It goes into the persistent memory-aware file system, and then there's this arrow that shows the file system has direct access to the persistent memory. So it can satisfy those reads and writes just by doing direct loads and stores to the media. And when the application memory maps a file using something like mmap on Linux or map view of file on Windows, then it gets this direct access without any page caching at all. And you can see we call that direct access DAX. So on this right-hand side, since it has all the standard APIs, I like to say this is also just like an SSD. You're just using persistent memory like an SSD, only there's no page cache in this case. And that's been possible for a long time using special interfaces, and memory mapping files has been around for a long time. And when you memory map those files and you store data to that memory, it's not necessarily persistent until you do something to make sure it makes it all the way to the media. It's always been this way on POSIX and in the Win32 APIs. And on typical storage, that means flushing the dirty pages out of the page cache. But on this direct access path, there is no page cache. So what do you flush? Well, those stores could still be sitting in the CPU cache. And so that's what you flush here. When you call msync, or it just flushes the range out of the CPU cache. So you get the same semantics that you would expect from POSIX, only what gets flushed is slightly different. Now, flushing the CPU cache is done with an instruction, and that instruction is not privileged. It can be done from user space. So this is the first time in my description now where I'm talking about an interface that's not an existing standard interface. We call this optimized flush, where you can just flush something to persistence directly from user space. And that's the interesting part that I'm going to focus on today. I'm going to kind of zero in on this optimized flush part. First of all, when you're programming to persistent memory, I think the general consensus is that flushing is somewhat painful. It can be error prone if you forget to do one of these flushes. Everything appears to work because more often than not, what happens is that that dirty cache line eventually makes its way to the persistence anyway, and you never really notice that you had a bug until you find a test where you can cut the power and prevent that from flushing at the exact moment where it's sitting dirty in the cache. It's very difficult to test like that. This kind of flushing, like I said before, it's not new. POSIX has always required it, and testing it has always been hard, even with POSIX. But at least the storage ecosystem is actually quite used to forcing things to go all the way to the media when they need to know, when they need to be assured that it's actually sitting on persistent media. So the question that we're here to talk about today is, can we get rid of this flushing? Can we just make it so you don't have to worry about it? And not to keep you in suspense, my answer is going to be maybe sometimes we can. So now with my Intel hat on, let's take some of those abstract concepts and talk about them more concretely. The Intel persistent memory product is called, you can see it here, Intel Optane PMem. And you can tell I worked with my marketing guys to get all those little R's and TM's things in the right place. And again, we define it very, very simply with the same 2 points as SNIA. It's byte addressable persistence, and its performance is fast enough that you reasonably wouldn't try to context switch away. So, if you think of the latency of a hard disk in say milliseconds, the latency of an SSD in say microseconds, we talk about the performance of persistent memory in nanoseconds. So it's sub-microsecond latencies typically. It's not 1 or 2 nanoseconds. Typically, it's more like 300, but it's still in that range, in the nanosecond range. How does persistent memory work on Intel platforms? Well, it plugs right into the memory bus. It's cache coherent, and that means that it essentially acts like memory. When you talk to it, you're doing the same load and store instructions. You're not worried about cache coherency because the hardware takes care of that. It's just like memory, only its performance is slightly different, and of course, it's persistent across power cycles. Now let's drill into that a little more. Here's a kind of a diagram of the path that a store takes towards persistent memory. So on Intel, a store instruction is called move, and you can see I showed here on the left side of the slide. I see the move instruction going through several layers of cache, and then down into this trapezoid here, which is the memory controller, which has a little queue in it called the right panning queue, and then down to the persistent memory DIMM right down at the bottom there. And so what we would really like to have happen is as soon as I issue that store instruction, it's persistent. But the reality of the situation is that would be pretty difficult to implement because these caches are hard to make persistent. I'm going to describe that in a lot more detail. So instead of the big dashed red box, which means this entire area is considered persistent, we require just the small dashed red box. And so all the platforms today, the Intel platforms that support persistent memory, do implement this small dashed red box. And that means if you get it across the line into the memory controller, then a store is then considered persistent. You can proceed under the assumption that it's persistent if you suddenly lose power. there is stored energy in the platform that'll make sure that store completes its journey and makes it all the way to the DIMM. So the way that you get something from the caches down into that small red box is, well, there's a couple ways. One is to flush the cache. And the most common way to do that is the CLWB instruction here. You do a CLWB on the address and then followed by a fence, and after that you can consider the store persistent. But there is also a special kind of store called non-temporal stores, which bypass the cache. And so there are times when that makes more sense, when you don't want to pollute the cache and you don't want to do that extra cache flushing step. You can just do those non-temporal stores from your application and then proceed. They also need to be followed by a fence, and then you proceed as if things are persistent. So when we first were defining the ACPI changes for persistent memory, where ACPI is how the operating system is told about the persistent memory in the system, we knew that we'd want to have this big red box someday, and that we were just starting around with a small red box. So we put a property in ACPI to indicate whether you can consider the caches persistent or not. And so if you kind of think of these two red boxes as having names, the small one is ADR, because that's the mechanism that is invoked when you want to flush the memory controller down to the DIMM. ADR stands for asynchronous DRAM refresh, which is not a helpful acronym at all. Instead, just think of it as ADR means that I flush the memory controller. And then EADR is extended ADR, where you'd actually get persistent CPU caches on Intel hardware. Going down kind of the next level then, at the platform level, like I said, we modified ACPI. We created a table in ACPI 6.0 called the NFIT, the NVDIMM firmware interface table, that reports all of the persistent memory installed in the system to the OS. And at the time, we also added a flag that says, this tells the OS if the CPU caches are automatically flushed on power loss. So that flag has been there forever, well, forever, at least for years now. And the OS abstracts it away, because we don't really want applications to open up these gnarly ACPI tables and have to parse them and look for every little detail. So we abstract away this information in a way that's easy for the application to consume. And now the application can just look, for example, on Linux, there's just an API that you call to say, are the CPU caches considered persistent? And you don't have to actually delve into those data structures. Later on, if we change where that information is stored, or let's say that we invent some new interconnects for persistent memory, again, this abstraction will hold, so the applications don't need to change. Okay. So when we're using persistent memory, there are lots of different ways to use it. There are certainly plenty of ways to use it where there's no flushing required at all. And so I put some of those ways on the left-hand side of this table. For example, the Intel product has something called memory mode, which just uses the capacity of persistent memory to make the system's main memory look huge. It doesn't require you to modify the OS or the application. You just see a huge memory machine. So that's transparent, volatile memory. Of course, it's volatile, so there's no need to flush anything because you don't care about persistence. And a surprisingly large number of use cases have come up where applications just want to use persistent memory directly for its capacity, and they don't care that it's persistent. And so they open up the file that I showed on the persistent memory aware file system, they memory map it, and they store stuff there that's not as latency sensitive as the stuff that they store in DRAM. But in both cases, they don't worry about it being persistent. They expect it to go away automatically when the program exits. And so that, I call that the volatile use of persistent memory. And it's actually a very big use case for us. And of course, it requires no app flushing. So there's really no pain point there. When you're using it as storage, as I mentioned before, storage has always needed you to do flushing of the page cache. That works the same way it always has. You don't have to worry about the individual flushing of stores to persistent memory. So all this stuff on the left is kind of too easy, right? It works fine, but to really leverage everything that persistent memory can do, what we've seen people do is modify their application to place data structures directly in persistent memory and then map them and maintain them in a persistently consistent form. You know, hash tables, trees, linked lists, whatever, these things live right in the persistent memory, and they are accessing those things with loads and stores and flushing as appropriate to make their changes persistent. And so the real question is, well, can we take that use case and kind of move it over to the left-hand side of the table where you don't have to worry about the flushing? Oh, let's see. What's so exciting about that? Why are people modifying their applications to do those data structures that live right in persistent memory? And it's because of the benefit that you get from fine-grained persistence. It's really about performance. To modify a single byte on modern storage, you have to read a block, you have to change the byte, and then write a block. And you know, on a modern disk, that's 4K. So you're reading 4K just to change one byte, and then you're writing an entire 4K just to change that byte, because that's your only choice. Storage operates in blocks. You can't just read a byte or write a byte. But to modify in, that same byte on persistent memory, you just go change the byte. Now, you know, and to be perfectly honest, on Intel hardware, we use cache lines when we talk to things on the memory bus. So that byte does get rounded up. There's still a read, modify, write. It's 64 bytes that get changed, and read in, change a byte, and then write 64 bytes. But that's still a lot less than 4K. And so you're saving all that bandwidth. That's a lot of I/O where you aren't moving data that you don't care about. You get that bandwidth back. You get to use it for other things. You get to use it to do more work. So it's a performance savings. And you know, if you think about making a data structure consistent, that's persistent all the time. Typically that's done with some sort of a transaction. For example, you might write log entries, but on storage, all you can do are write these 4K log entries, right? And there's been a lot of work over the past decades on optimizing that as much as you can, and making those logs be as optimal as possible, but you still have to write them in big chunks. But with persistent memory, you have this fine-grained updates. You can make a log that has 64 byte entries in it, or you can even do some more clever programming where you don't need to log by doing shadow pointers or some other things that we'll talk about in a little bit. So this is the benefit of the fine-grained persistence. You get to do these things that literally aren't possible in storage, but they're still memory-like and they're still persistent. So it's pretty neat. So now, what is this idea of the persistent CPU caches? Another term for this is flush on fail. So what is that? Well, flush on fail is not a new idea. For example, lots of types of storage have write caches. They're more performant, and the idea is that when the system is coming down, they get flushed out. And so even if you lose power, the best effort is made to flush those things on fail. Now, on some storage devices, those caches aren't guaranteed to be persistent, and on some they are. It really depends on the device. So for example, on an old hard drive, usually there was some sort of a flush the write buffer command that if you really needed to know that something was guaranteed persistent, you had to issue that flush. On the other hand, a lot of SSDs in their implementation have a write buffer inside that is power fail protected, and they use that to gather up information into chunks where they can write it to the media. So like I say, flush on fail is not particularly new. You could even consider the NVDIMM-Ns that have been on the market for some time now to be doing that, you know, during runtime, you're just doing I/O to DRAM. And then when they detect power loss, they flush all that information to a flash chip. So not particularly a new idea, but it is something that does add some complexity to the system. So why didn't we just do this from the beginning? I remember my diagram earlier with the small red dashed box and large red dashed box. Why didn't we just make the CPU caches persistent from the beginning? Well, of course, the answer is cost. There's quite a bit of stored energy required in order to make those things flush when you lose power. You have to keep all of the cores running to execute the flushes. In other words, the CPU cores, you know, they manage the coherent cache. So they know where the cache lines are. They know which ones are dirty. They have instructions that go through and find all the dirty lines. So you have to run those instructions on power loss. So that means as soon as your as soon as your system detects power loss, it has to have enough power to then power both the cores and the memory subsystem long enough to do that flush. So that's more than just some little capacitor in the power supply like we had for ADR. For EADR, we probably need a battery. right? Something with a lot more stored energy. And batteries have a higher cost. They have a higher failure rate than a lot of the other parts in the system, so there's a maintenance burden. So if you're going to put a battery in a system, you're going to charge more for that system, and you have to have a really good reason to want people to pay more. And so for flush on fail caches, that reason is performance, which I'll show you in a minute, what that really means. And you have to weigh the cost of adding the battery to the system to the gain that you get from the performance. Now, that equation isn't quite clear until people establish some software and get some performance numbers. So we always knew that in the beginning there would be the less expensive systems that don't have a battery in them. And in fact, all the systems that ship today for persistent memory are like that for the Intel systems, because they implement that required smaller dash red box. But in an upcoming generation, pretty soon now, you're going to start to see systems that implement the large dashed red box, and you'll make a decision on which system to use based on the benefit of the performance gain. So in a world where CPU caches are persistent, what does that really mean? What does the world look like? So what I like to do is talk about the difference between visibility of a store and persistence of that store. And in today's systems where the CPU caches are coherent, so other threads running on other cores, they do see your changes. That's different from when something becomes persistent, when it's flushed from the CPU cache. So let's delve down into a kind of a simplistic, this is almost pseudocode assembly language here, because I took some liberties to try and keep it simple. But you can see my idea here is I've got a variable x and y that are living in persistent memory. So here I am storing 10 to x in persistent memory. Here I am storing 20 to y in persistent memory. And you can see before I've done anything else, if I just go and read x, I take x's value and I put it into the EAX register, I'm going to see 10 because my changes are visible, right? They are visible, but they're not necessarily persistent. Now, they might be persistent because normal system activity might end up just flushing those things, evicting those things from the cache. So I'm not guaranteed that they're persistent, and I'm not guaranteed that they're not persistent. They're in this state where they might be persistent. To ensure they're persistent, I have to make sure they're flushed from the CPU caches. And to do that, I use the CLWB instruction that I mentioned earlier. Assuming these two locations are in different cache lines, I have to do one CLWB for each cache line that I'm trying to flush. And then the CLWB instructions are launched. They start asynchronously. So to know that they're finished, you have to issue a store fence. Once you've issued that store fence, you now know that these two stores are considered persistent. Even if you lost power on the next instruction of this program, those values would persist. They're in the persistent domain at that point. So this kind of describes how persistence has worked for the first generation of the Intel Optane persistent memory, and for the NVDIMM-Ns that have been out there for years. This is the model for how you program these things on Intel. Now, when you have those flush on fail caches, now visibility and persistence happen at the same time. Almost. The devil's always in the details. So let's go through it. So here I am again storing 10 to x, and I'm storing 20 to y. And sure enough, if I load from x into my EAX register, I see the 10. So it's visible. And maybe it's actually persistent, because since it's visible at this point, that means it's part of the cache coherency architecture. That means if I were to lose power right now, it would indeed get flushed and be on persistence. So why am I being kind of wishy-washy about this? Because like I say, the devil's in the details. If some of these move instructions are not just traditional move instructions like I'm showing here, but they're the non-temporal move instructions I mentioned earlier, which go around the cache, then you really do need the fence. The fence is part of making a non-temporal instruction visible. Non-temporal instructions are actually not cache coherent until you hit the fence. So when in doubt, if you're not quite sure whether something is the code that you're doing is leaving something in a persistent state, put the fence in. But there are some cases here where you can technically leave the fence out. The easiest thing to do is actually just use a library like PMDK, where we've painstakingly gone through, figured out where the fence should be, and you benefit from all that work. So when visibility equals persistence, most notably, there are no CLWBs over here. And remember that the CLWB instruction is a double-edged sword right over here. The CLWB instruction on the currently shipping Intel hardware also invalidates the line in the cache. And so it kind of has two effects. It not only flushes it to persistence, but the next time you access that variable, it will be a cache miss, and you'll have to pull it back in. So by avoiding the CLWBs over here, not only do you not wait for the cache to flush for the writes, but you leave it in the cache for the next access to make that faster too. So it's kind of doubly good when visibility equals persistence. So let's talk about the actual performance benefit. Now, what we did is we took a version of Cassandra and we modified it for persistent memory to do its thing in persistent memory. And then we took it to a system, just a currently available system with ADR, and we ran it, gathered the results, and then we told it to assume that the system has EADR. Now, we built this on top of PMDK, Persistent Memory Development Kit. It has a facility in it already where you can just set an environment variable, and it will assume that the system has EADR, and then you can run that for benchmarking. As long as you don't actually remove power, you can use this to gather a performance projection on what performance you would see with EADR. So you don't actually need a system with EADR to figure out how much you'll benefit from it. It's actually pretty easy to do. And over on the right here, you can kind of see the results. Now, because this version of Cassandra is one that we modified, and it's not the currently publicly shipping available version of Cassandra, I wanted to be kind of cautious about giving you the exact numbers. So I blocked out the numbers here, and I just wanted to show you relative performance here, just because I was trying to be kind of cautious, not to promise something until it's completely available to everybody. But here you can see when we are creating a data set with 200 threads and 12 million records, you can see the blue represents the operations per second that you get on a normal ADR system where you're doing cache flushes. The orange represents how many operations per second you're getting, and higher is better, and you can see it's quite a bit higher. So you really do get quite a benefit from being able to skip those cache flushes. If I'm doing a write-heavy workload, again, you would expect that there are a lot of flushes in a write workload, and of course there are. So by skipping those and letting them evict from the cache on their own, you again get quite a benefit there. And it's the same semantics, right? You still get the same end result. The same things are persistent at the end in both cases. It's just that in the orange bar, you didn't have to do the cache flushes because you had EADR, you had flush on fail caches. But of course, if I adjust the workload to be more reads and fewer writes, like there's one with 8 reads for every 2 writes, then you can see the benefit is less, right? The more writes you have, the better the benefit will be. That makes sense because your writes have flushes going along with them. Reads don't need flushes. Kind of a similar picture on the latency. On latency, lower is better on the graph. So again, you can see the blue here with ADR, and then the orange with EADR improved quite a bit on the data set creation case. And again, you can see the more writes you have, the better the improvement is on latency as well. But the bandwidth is really, I think, more dramatic of a performance improvement that you get with these flush on fail caches. So, okay, great. So you get performance. Now, what else happens when you have flush on fail caches? Well, let me tell you a story of a couple of the mechanisms that don't quite work in persistent memory, the way that persistent memory is implemented today. One of them is called non-blocking algorithms. Sometimes people call them lock-free algorithms, but I actually prefer the term non-blocking because they really are boiled down to depending on this compare and swap operation. And in Intel, the compare and swap instruction is called lock compare exchange. Notice it has the word lock right in it. It's like a very tiny lock that happens just during one instruction. So it's not quite lock-free. It's really just Now you have one instruction that's doing something atomically, and that's the only real locking that happens. Above that, it doesn't ever grab a lock or wait for someone to release a lock, so it's non-blocking. And a compare and swap, I've kind of outlined it in this pseudocode over here on the right on how it works. You give it an address, and it goes and it fetches the value at that address, and then it looks to see if the value was the existing old value that you expected. And if it was, it goes ahead and sets the new value. Otherwise, it doesn't, and then it returns to you what the value it was that it fetched. So this way, the idea is you can use a compare and swap to say, if nobody has changed this since I last looked at it, then it's okay for me to change it again because I already know that you know what the state is. So I'm making all the right assumptions about changing it to its new state. But if somebody's gotten in here and made a change, then my state is out of date and I got to go resync and try it again. So usually these non-blocking algorithms have a little loop where they go back and resync, and that's the rare path, and the common path is that they find that nobody has changed it and they just proceed without the traditional kind of locking. The problem with persistent memory, if that byte that you're, or that value that you're doing the lock compare exchange on, if it lives in persistent memory, well, there's no instruction that does an atomic compare, exchange, and flush, right? So that's kind of a problem because now you've got this algorithm that you wrote for volatile memory. You bring it over to run it on persistent memory. It doesn't quite work because you could proceed on the assumption that you made the change to that value, and then you get a power failure. You come back, and since your change wasn't persistent yet, you've made calculations based on the wrong assumption. So, of course, there are ways to fix this. You can change your non-blocking algorithm to be a PMem aware version of that algorithm. One example of this is to do a sort of a flush on read, where every time before you do a lock compare exchange, you read the value, you flush the value to make sure that what you are going to read on this instruction comes from persistence. But of course, that has a performance overhead. Like I said before, the flush also ends up invalidating it. So that means, you know, you're taking this location that might even be a very hotly accessed location because it's used for coordinating this algorithm, and you're flushing it out of the cache and invalidating it right before you read it, so you've got to go read it again from the media. And so that can really impose some overhead. But worst of all, you've got now a persistent memory aware version of the algorithm that's different from your volatile version of the algorithm. So that also is kind of annoying. So that's been a problem with this traditionally. Another mechanism like this is called RTM, or for restricted transactional memory. This is a feature that has, in the Intel processor, it has an XBegin and an XEnd instruction. And the stuff in between those two instructions is like a little mini transaction. You do an XBegin and you make some changes, and the CPU caches are recording the changes that you're making in your local cache. And when you do the XEnd, if nobody else has interfered with those changes, then everything is good and you just keep running. So it's kind of optimistic locking. On the other hand, if in the middle of your transaction somebody else messes with something that you've been, you know, frozen in your cache like that, then you get an abort, a transaction abort. And there's a little instruction called xabort where you write the handler, the xabort handler. And what you're supposed to do in that handler is fall back to traditional locking, where you go and actually just grab a mutex and do the change the hard way. It doesn't really result in getting rid of locks. It results in getting rid of locks in the optimistic case, and you know, optimizing the path. But since it uses the cache the way I was talking about to hold the state of what it's doing, a cache flush is one of the instructions that'll always cause an xabort. So if you do an xbegin and you're starting your algorithm and then you say, oh, now I need to make this persistent, and you put a CLWB in there, you'll get an xabort, and now you're back to traditional locking. So that's why these RTM instructions aren't typically used with persistent memory. So in a world where now visibility is equal to persistence, maybe these things change, right? So first of all, lock compare exchange now works as expected because, you know, I mentioned before, there isn't an instruction that says lock, that says compare, exchange, and flush all at once. Well, now there is, because just making something visible makes it persistent. So when you do this compare exchange, as soon as it's done, as soon as the atomic extraction is done, the result is in fact persistent. So that's great. And now you can actually write a piece of code that works in volatile memory as well as it works in persistent memory, except it doesn't solve other things. Now, when you start looking at these non-blocking algorithms, you will find pieces of code that translate just fine. You can move them from volatile memory to persistent memory when you have something like EADR. But you'll also find plenty of code that has some volatile memory assumptions in it. For example, let's say I have an algorithm where somebody is allocating a new node and attaching it to a linked list using a non-blocking algorithm. So I allocate the new node, I fill it in, and then using lock compare exchange, I adjust the pointers in a very careful way to put it in place. Now, if I die in the middle of that, the list is perfectly consistent, right? It's healthy because my lock compare exchange was carefully coded to make that true. On the other hand, the memory that I allocated never got linked in anywhere, so it's leaked. So that's not quite right. And it's because a lot of these, like I say, a lot of these algorithms have this assumption that, well, this is volatile memory. So if I get interrupted here, the program will start over again and the memory's all cleared out. So I don't have to worry about things that I allocated it didn't use. Now, even if you have a garbage collected language like Java, the current Java implementation of its memory allocator and its garbage collector are written full of volatile memory assumptions, right? They're not written for persistent memory. We'll change that over time, I hope. But I just want to make it clear that while some things will translate directly from a volatile memory to persistent memory, you really have to look at each algorithm carefully to see if there are volatile memory assumptions in there. Similarly with RTM, it can work. And now that you have visibility equal persistence, when everything goes fine, it works great. But when you have the export and you fall back to traditional locks require special handling for persistent memory, because part of holding a traditional lock is the state of where your code is executing, because you know that at some point you're going to go back to the part where you release the lock. So these locks in persistent memory need either some sort of handler on recovery that looks at them and figures out how to unlock them, or they need to automatically reset or something, right? Libraries like PMDK have special locks that you can use when they reside in persistent memory, and they automatically reset when the transaction gets rolled back. So XBegin and XEnd, they can work. They don't quite just work like they do on volatile memory. So the inconvenient truth then, in summary, is that most code that's written for volatile memory is riddled with volatile memory assumptions like memory allocators or garbage collectors. And persisting the memory doesn't persist the thread state like the instruction pointer in the stack. And that's an important part of a lock state. If somebody grabs a lock, the fact that they're executing the code in the critical section is kind of part of the overall state. It's a pretty important part because at the end of the critical section is where you release that lock. And if the system loses power, the lock was persisted, but not the rest of the thread state. And as I mentioned before, there's a big cost trade-off here, and people will be shipping platforms that have just ADR and not EADR for a long time. Now, you could run an application that only works with the ADR. It checks the ACPI property and bails out. Says, I can't run on this. You don't have EADR. But I think you'd be reducing the usefulness of persistent memory for that application because, there are going to be systems of both types for a long time. So the bottom line here is that I see EADR as a means to get better performance. You saw my Cassandra numbers. The performance is better, but not simpler code. You're still going to have code that decides whether it needs to do flushing or not. So it doesn't actually just remove all the flushes from your code, but it does mean when the flushes aren't required, your code's going to be faster. So that's, to me, is the bottom line here. Now, I'd like to diagram the summary that I just gave as a set of responsibilities that the application has. And this is an important part of our programming model. It's been part of the programming model all along, and in all of the sessions we do about the programming model, I always show this diagram. The details aren't that important. You can find this diagram in my slides or online if you want to go through it more carefully, but mostly you can see in the middle here is a question: are the CPU caches considered persistent? And if they are, then you don't have to worry about the flushes. You can just consider things persistent as soon as they're globally observable. On the other hand, if the caches are not considered persistent, you're back into this cache flushing mechanism. So for every mechanism that we invent in a computer system, we need to think about what happens when it fails. And flush on fail is no different. Flush on fail can fail. So what happens? So we've always had flush on fail in persistent memory programming, in modern day persistent memory programming. We've always had ADR, right? ADR is required. The NVDIMM-Ns that have been shipping for a long time and the current Intel product, they require ADR. And that's to flush the write pending queues in the memory controller. And if that doesn't happen, if something fails, like a hardware problem or something, you don't want silent data corruption. When the system comes back up, you want to notify the application that there's something that went wrong and that your data is in an unknown state. We call that a dirty shutdown, and we expose that to applications in our programming model through something called a dirty shutdown count. So when we decided to introduce EADR, we wanted to make sure that applications didn't have to have yet another check. Let's not have an application check for every kind of little mechanism that gets invented over the years. That would start to get really tedious and require application modifications each time. So EADR uses the very same mechanism, and software just looks at the dirty shutdown count. If the dirty shutdown count says that you've had a failure, it could be an ADR failure, it could be an EADR failure, but it's the same as far as software is concerned. And so, I always show a second little table then, a flow chart of application responsibilities, making it clear that part of the programming model is checking for a dirty shutdown. This is part of the programming model today, right? This has nothing to do with EADR, except the fact that it will be the same under EADR. So if you're writing an application for persistent memory and you're not doing these checks for dirty shutdown or for whether CPU caches are flush on fail, you should be. They're part of the programming model. Or you should be using libraries like PMDK, which do these checks for you automatically. So there's an aspect of this flush on fail where you have to gain the trust of the ecosystem. And the good news is that these dirty shutdown cases, which sound kind of scary, are rare. They're intended to be on the order of a device failure. How often do you have to replace a DIMM in your server? It happens, but it's not super frequent because the machines and the DIMMs are pretty reliable these days. And so people trust in that reliability, and they know as long as they are notified when the things fail, they can mostly just write their code assuming that they're not going to fail, and that they can just handle the failure case as a data loss, where they go and get data from a backup or reconstruct data from a redundant copy. So that's kind of the idea here with dirty shutdowns. They're rare. Think of them like, well, the device failed and you lost your data, go get it from a backup copy. That's kind of bad news because, like I say, when flush on fail fails, you really are in an unknown state. It doesn't fail like by rolling back your last transaction. It fails by flushing or not flushing some unknown amount of data. You have no idea which things got flushed and which didn't, and you have all ordering information between the stores has been lost. So it is bad news when it flushes. It does mean that your data is gone. You should be restoring it either because you've been doing things like some sort of RAID or erasure coding to maintain a redundant copy, or because you keep a backup snapshot every now and then, however you want it. But I am convinced that the success of EADR is really tied to gaining this trust. In other words, thinking of this as a very reliable mechanism that it fails very rarely. So far, ADR has really kept up to that promise. The failures are extremely rare in what we've been shipping for the last 18 months. And so I'm happy to report that. And my intention is to make sure that EADR turns out the same way. So that was a lot of information, a lot of background. Are there things that we can do to make this persistent memory programming even easier? So as I've mentioned a few times already, we have the persistent memory development kit. It already comprehends this idea of persistent CPU caches. It checks for it. It knows when it can remove flushes and when it has to use them. It has heuristics in it that decide when to use non-temporal stores and so on. The code is free. It's open source. We put a very liberal license on it, so you're free to steal it, rip the code out, put it into a closed source product. We don't care. We're not trying to make money from PMDK. We're trying to make persistent memory programming easier. We spent 5 or 6 years now on PMDK. It's actually been a number of years. It's been part of a lot of Linux distros for many years. It's available on Windows. And we learned a lot doing this. We learned a huge amount doing PMDK. So over the past year, we took all that stuff that we learned, and a bunch of us got together and wrote a book about it, coordinated by my coworker, Steve Scargill. The book is about persistent memory programming. It describes pretty much everything that I've been describing in this talk. And the book is free. It's online. You can read it for free, or you can pay the printing costs and get a copy. And you just find it by going to pmem.io. So the real point that I'm trying to make here is that even if you don't have a machine today that has persistent CPU caches, they're coming soon. You should be programming for them today by either using a library that already knows how to do it, or doing it yourself in the way that I described in this talk. So one last thing I wanted to point out is that the loss of power is something that is not actually a big consideration in some environments. And this was kind of an interesting thing I learned when I started looking into this. Instead of a battery for the stored energy that we need for EADR, couldn't we just use a UPS? Why not? UPSs, I can go down to Staples and buy one, right? They're pretty easy to come by. And when the UPS loses power, it continues to supply my server with power, so the server keeps running. The UPS can tell the server, hey, I lost power. And the server can just do a nice normal shutdown, flushing everything as normal. So in this version of EADR, all shutdowns are normal, at least as far as persistent memory is concerned, right? They all have orderly flushes. There's no sudden loss of power to the server. The server decides when to power itself off because it gets such an early notification of power loss that it has minutes, or as many as we decide it needs, to do the shutdown. This is kind of an intriguing idea, but there are a few issues that came up when we looked into doing this. And they're not insurmountable issues. I still think this is a good idea, but you have to consider the whole picture, right? First of all, the BIOS is the one that reports to the OS whether the CPU caches are persistent or not. And that's how an application knows, by looking at the ACPI table, knows whether to flush the CPU caches or not. So it knows if the platform has EADR because it's the platform BIOS. What it doesn't know is if the system has a UPS, or how loaded the UPS is, like how much energy is in the UPS. So do we need to make standards where the BIOS can talk to a UPS and discover it and find it? And I started down that road for a little while. But what I really found is that the modern UPS and these big data centers and big cloud providers aren't really these things that you buy down at Staples anymore. There's not a UPS sitting next to every machine. Instead, they have these data center-wide UPSs. Unless you're like a doctor's office server, you don't really have the kind of traditional UPS. They're just not that common anymore. And so for these big enterprise-like customers that I'm targeting, all these shutdowns are orderly shutdowns because they basically never have power failures, except when they do, and when they do, they kind of consider them dirty anyway. So it's kind of a different world. And how to handle that? Well, we're looking at a way of detecting that you're in that kind of a world and reporting that it's safe to consider your CPU caches persistent. But it's an area that needs a little work. Okay, so in summary, I used to come here for the past 6 years and say, persistent memory machines are coming, but now, a year and a half ago, we started shipping them, and they've been available for quite a while. Then I started saying, well, and all the ISVs are going to adapt their software to it. Well, actually, that's happened with quite a number of applications now, so fairly major ISVs. And I know of dozens of applications and hundreds of people investigating it. So there's quite a bit of work going on. So now I'm here to tell you, persistent CPU caches are coming. Really, they are, and I think this is actually coming very soon. Because of the timing of SDC, I couldn't give you the exact platform that they're going to be coming on, but it's soon. So if you follow the programming model, you will benefit from those persistent CPU caches. That's my bottom line. Okay, that's my talk. Please take a moment to rate this session. Your feedback is important to us, and I hope you enjoyed this talk.